Hi, everybody. Today we are talking about kites and trapezoids, okay, and their properties. So first we're going to start with a kite. So a kite is a quadrilateral, so it's got four sides with exactly two distinct pairs of congruent consecutive sides. So a kite looks like this. It's got four sides. It's got two pairs of adjacent congruent sides. So this side, these two sides are adjacent, they're next to each other, they're congruent. These two sides are adjacent, they're next to each other, they're congruent. These two angles along this axis right here are called vertex angles. These are called non-vertex angles. Okay? So this one, K-I-T-E, is a kite. Oops. Okay. So what are some of the properties of the kites? Well, the non-vertex angles of a kite are congruent. So what we're saying here is if we have kite MNOP and they have vertex angles M and O, then angle P has to be equal to angle N. Okay, so the first thing you're going to do is identify the non-vertex angles here. So that would be angle P and angle N. Okay, so how do we prove this? Well, what we would do is we would start out by drawing this right here. We're going to draw the diagonal that's down the axis of the kite. Okay? And now we know that PM is congruent to NM. And so these two sides are equal. And we also know that that PO is congruent to NO. So this side is equal to this side. And the reason that we know this is both of these definition of a kite. Okay, if it's a kite, then it has two distinct pairs of congruent sides, adjacent congruent sides. Okay, now next, we know this. We know that MO is congruent to MO by the reflexive property. Okay, so now that gives me two congruent triangles. So I've got triangle MPO is now congruent to triangle MNO by side, side, side. So the triangles are congruent, and now we can finish this off with this. Angle P is congruent to angle N by CP, CT, C. Okay, so these have to be congruent because they're corresponding parts of congruent triangles, and so they must be congruent. And I'm done. Okay, so we proved one of the properties of a kite. All right, theorem. The diagonal connecting the vertex angles of a kite is the perpendicular bisector of the other diagonal and is also an angle bisector of the vertex angles. So this says two things. It says, first of all, it's this one here, since it's the diagonal that connects the vertex angles. It is the perpendicular bisector, so it's a 90-degree angle here, and those two are equal of the other diagonal. And it also says that it's the angle bisector of the vertex angle. So those two angles are equal, and these two angles are also equal. And that's true all the time. Now, a rhombus is just a special kite where all four sides are equal. And so that's going to be true over here, too. This is going to be the perpendicular bisector of that. And it's also going to be the perpendicular bisector of this. Okay, because either set with a rhombus, since all four sides are equal, either set of angles could be either these two or these two could be the vertex angles. Okay, and then in this case, all four of these angles are equal, and all four of these angles are equal. Okay, so there we go. Now let's talk about a trapezoid. So a trapezoid is a quadrilateral with exactly one pair of parallel sides. Okay, so here we've got a couple of trapezoids. Okay, this one appears to be an isosceles trapezoid, which is a trapezoid where the two legs are equal. It is not. It does not say that two sides are equal, because that could be this side, and this could be different. That would not be an isosceles trapezoid. It's only if the two legs are equal. So the two non-parallel sides are the legs. So this would be a leg, and this would be a leg. Okay. So the parallel sides of a trapezoid are called the bases. So this would be a base. This is also a base. This is a base. This is a base. Okay. The sides of a trapezoid that are not parallel are called legs. So over here, this would be a leg, and this would be a leg because they're not parallel. A pair of angles that share a base as a common side are called base angles. Okay, so here's the thing. Let's see. These two angles right here are base angles. And in this case, since this is an isosceles trapezoid, they're equal. Okay. And then also these would be base angles. And again, since it's isosceles, those are going to be equal. Okay. Now, these two here would not be base angles because they don't share the same base. So base angles here would be this angle and this angle, and base angles here would be this one and this one. Okay. Okay. Theorem. The consecutive angles between the bases of a trapezoid are supplementary. Okay, so here we have GHJK. Okay, so what this says is angle G and angle H are supplementary. And it also says that angle K and angle J would be supplementary. So they would add up to 180 degrees. We got a little proof here. Okay. So we're given trapezoid GHJK, and GK is parallel to HJ. Prove that angle 1 and angle 2 add up to 180 degrees, and that angle K and plus angle J is 180 degrees. So here we go. Remember, these are parallel lines, and there's a transversal right here. So we know this. Let's put a couple other angles on here. Let's put a 3 right here. Okay. And so we know that angle 2 is equal to angle 3. Okay, so this angle is equal to this angle. And that's because parallel lines imply that alternate interior angles must be equal. Okay? So, we also know that angle 3 plus angle 1 adds up to 180 degrees because they are a linear pair. Now, if angle 3 plus angle 1 is 180 degrees, and angle 2 is equal to angle 3, we can substitute angle 2 for angle 3 here. Okay, so this is substitution. And now we know that angle 1 plus angle 2 is 180 degrees, so we've proven that. Now what we can say, so we don't have to do this all over again, is we can say, similarly, for angle K equal to angle J. Okay? So what that means, of course, is we could do this exact same thing by just extending this side over here like we did this one. And we can do the exact same proof here, only on the other side. And so we don't have to do all these steps over again. We just do one. So we've proven that. And so what we've proven is that two angles that are between two parallel lines that are not the same base angles have to be supplementary. Okay, an isosceles trapezoid is a trapezoid where the legs are congruent. So here we have a nice WXYZ is a nice isosceles trapezoid. And again, here we have the legs. They're equal. Now be careful. Like I said before, you can't just say two sides are equal, because that would make this an isosceles trapezoid, and that's not an isosceles trapezoid. Okay, so we're just going to make that go away. Okay, the base angles of an isosceles trapezoid are congruent. So we talked about this a little bit. That tells me that angle W and angle Z are equal. And it also tells me that angle X and angle Y have to be equal. Okay. Alrighty then. The diagonals of an isosceles trapezoid have to be congruent. Okay, so in this case, that says that PR has to be congruent to SQ. Okay, we could prove that pretty simply. We could look at this triangle right here, and we can compare that to this triangle right. That's not the right one. Not that one. And undo. Let's try this one. This triangle. Okay, we can prove that those two triangles are congruent because these two sides are already equal to each other. Okay, so we know that PQ is congruent to SR by definition of an isosceles triangle, or isosceles trapezoid. Sorry, making my two-column proof right here. We can say that QR is equal to itself. QR is congruent to QR by reflexive. Okay, we've already shown that that the base angles of an isosceles trapezoid are congruent, so we can say this. We can say that angle Q in the yellow triangle is equal to angle R of the green triangle. So we would say the base angles of an isosceles trapezoid are equal. That was a theorem we had earlier. Now look at this. In the yellow triangle, we have side, angle, side. And in the green triangle, we have side, angle, side. So we can say that angle triangle PQR is congruent to triangle SRQ by side angle side. Okay, and then that just means that PR has to be, that's in the yellow triangle, has to be equal to SQ of the green triangle by corresponding parts of congruent triangles are congruent. CP, CTC. And we're done. So we've proven this theorem right here. Okay, got a little assignment for you. Have fun with that, and I will talk with you guys later.